Okay, good morning, class. So, in the previous classes, we have discussed regarding the gate level modeling and data flow modelings. Now we have to go with the behavioral modeling. Okay, so you can see here this design description at a data flow level or the gate level is very much near to the circuit, right? We will be we will be writing the code by seeing the circuit itself. The coding will be very much near to the circuit, right? So when we go with the behavioral modeling, uh, here in the behavioral modeling, we will be mostly using the loops also. If condition like this, we will be using some if conditions. If so and so thing happens, you execute this set of statements. If so and so thing happens, you execute this set of statements like this. In the VHDL also, you can observe that we have four modeling styles: data flow, behavioral, structural, and the hybrid model. Okay, so in the VHDL, for writing the code in the data flow model, we just require the expressions. Okay, we have an expression and we simply write that expression as an VHDL code and we will get the uh, output, right? In the in the structural model also, you can see by seeing the structure itself, we can write the program. In the behavioral modeling, you can see in the behavioral modeling, we will be writing the behavioral modeling code with the help of the truth table. That means we are defining by seeing the truth table, we can define if A is 0 and B is 0 and C is 0, the output Z should be 0. Okay, like this. If A is 0, B is 0 and C is 1, the output Z is equal to 1, like this. That means you are defining the behavior, so we call it as a behavioral model. In the similar fashion in the Verilog HDL also the same thing will be continued, right? So the data flow level or the gate level will be very much close to the circuit, but this behavioral modeling is a little bit different. uh, we have tried the code which we can't see also in this behavioral modeling. Do you know, do you understand that in the circuit we can't mention if so and so is true, if so on it has to go like this. Generally this thing will be written with the help of a flow chart, what we have studied in the C language or else in the VHDL also. That by seeing the flow chart, if so and so thing happens, it has to execute this set of statements. If so and so thing happens, this has to execute this set of statements like this, right? So you can see, just if we go with the introduction, just we'll see this introduction once. So design description at the data flow level and the gate level are close to the circuit. Okay. So at every stage of the design description process, one can relate the modules and the instantiations with the corresponding logic or sequential blocks and their interconnections. Okay. Approach is practical and effective as long as gate count remains in a few hundreds. In few hundred, right? Okay. If the number of gates count increases, we can still accommodate. This is due to generally increase in the vector size. What is this vector? Vector size means that means that the number of inputs got increased. If the inputs got increased, we call it as there is an increase in the vector size. When a system designed and tested at a 8-bit level is being scaled to 16 or 32-bit level, okay, that means there is an increase in the vector size, right? Initially it is of 8-bit only. Now we are increasing it, the number of bits of input to the 16 or 32-bit. Okay. So in the previous discussions, we also have seen that the compiler size the number of input bits will be depending upon the compiler bit size, right? If the compiler is of 32 bit or 64 bit, at most we can give only 64 bits or 32 bits correspondingly, right? So if it is a 32 bit compiler, then we can give only 32 bits inputs. If it is 64 bit compiler, then we can have the possibility of giving 64 bit inputs also, right? So generally this gate level or data flow levels will be helpful for designing the smaller scale designs. So this there is a huge increase in the functionality of the circuit. It becomes typical to do the design in the data flow level or in the gate level, right? So behavioral level modeling, you can see. So in the behavior level modeling, what we can see, you can see here now, behavior level modeling constitutes design description at an abstract level. Okay, it is going to describe at the abstract level. That means abstract means we are explaining some content. That means it at this particular point of time, it is going to give this output. It has to give this output. It has to give this output. Okay, that is called abstract level. Okay, one can visualize the circuit in terms of key modular functions and their behavior. It can be described at the functional level itself instead of getting bogged down with implementation details. So if you go with this Verilog HDL coding, it will be similar to that of our C language coding. So in the C language also, we will be mostly describing in the behavioral model. Okay. The C language also, when we learn the C language, we have never initiated this type of whether it is data flow model or behavioral model or structural model, whatever it may be. But just we have assigned some values. We used to assign some values. Some I is equal to 0. Okay, C is equal to I plus plus. Like this, we have used this type of statements in the C language. The similar fashion, such type of statements can be the Verilog coding will be similar to that of our C language mostly. Okay, so here as an example, one can describe an FFT fast fast Fourier transform or a digital filter routine in terms of these constructs also, right? Okay, that means what we are doing, we are describing the functionality of the FFT. We are describing the functionality of the FFT, that is with the help of the constructs. Constructs means what? Constructs means syntax, right? With the help of syntax, we are going to describe the functionality of FFT also. So we can write the coding and we can simulate it and we can debug it. So first we have to debug and then we have to simulate it. So what what we can see here is after doing all this, it completes the system level structure of the design. Okay, we will design one content and that can be used multiple number of times. Right? That is what we have seen in the structural modeling of VHDL also. The similar fashion also we can go with this Verilog also. We will do some basic level, what you say, some basic level programs, and later we can further expand it by using that one multiple number of times. For example, if you remember, for designing a parallel ladder, what we have done, We have first we have prepared the full ladder, and we used just if you, for example, if you are designing a 4-bit parallel ladder, we have taken 4 full ladders in physical in the circuit. But when you write the coding in the structural model, you have written only one full ladder program, and you have called that full ladder program 4 times, since it is a 4-bit full ladder, right? The full 4-bit parallel ladder. So in the similar fashion here in this Verilog HL also, the same thing will be going to work, right? So what we do is we describe the content. Here you have taken example of FFT. First you used to describe it, and you will be constructing, you will design, and you'll simulate it, debug, and we can finalize it, right? So what is this? First we will debug, then we will first what we do is first we will verify the syntax, that is compiling, right? If compilation is okay, that means where there are no syntax errors, then we will go for the simulation, right? We will see that whether we are getting properly the outputs for the corresponding inputs or not. By verifying that, if you find any fault in the output, you have to debug it. That means you have to verify the code, and you have to verify it, and you have to change it, and then once again you can compile and you can simulate, and at last if you get the correct output, you have to finalize it, right? That code is correct, and then that code can be called in another programs many number of times, right? So that coding or the particular program, that particular program may be in the data flow model, or gate level model, or this behavioral model, whatever it may be. Okay, if it is very log type code. If it is a VHDL type, any of the data flow, behavioral, structural, or hybrid, whatever it may be, like that. So, so there you have designed the full ladder, and then you have expanded it to the parallel ladder by connecting in correct sequence. So what we'll do is we can simulate, debug each such components modules, check it for the functionality, integrate it with the main designs, integrate it with the main designs, and test for the conformity, right? So that's the thing what we have done. So when we are willing to write the 4-bit parallel ladder, first what you have done, you have done the full ladder, right? So you have done the full ladder in the either the behavioral model or data flow model. If at all, if you want to do the total thing in the structural model only from basic gate onwards, if it is the condition, you have for designing of the full ladder also, you have to design the full ladder has to be designed with the help of the half ladders only. If it is the condition of making the full ladder also with the half ladders, right? And then if the full ladder is ready, that means if you have finalized the code of the full ladder, that means finalizing the code means you have verified the functionality, and you have checked the syntax, compiled, you have checked the syntax, compiled, and then simulated, and then you have debugged, and if you have any mistakes you have debugged, and then you have finalized the code, and that one, then only we can say that it is finalized code. So that finalized code of full ladder will be used in this parallel ladders, right? So check it for the that means integrating it means, so okay, you have integrated all these 4 full ladders, and then you have to verify once again, and you have to confirm whether it is in the correct form or not. Proceeding with the layered expansion of the design, one can have the final design description at the RTL level. Okay. So here we may add here at such a top activity is more in the realm of the design, right? So RTL actually in the Verilog we can have RTL level design. Okay, Verilog will be helpful in designing of RTL. What is RTL? Register transistor level design. Register transistor level design. This is possible in the Verilog only, right? In the VHDL we can design only up to the gate level design. Okay, so minimum level circuit in the code you can write only for the gate. That is the gate what we have written at the minimum level is the inverter only, right? But in the Verilog we have the chance of writing at the transistor level also, register transistor level. That is called as register transistor level, right? So the constructs available in the behavioral modeling aim at the system level description. Okay, the constructs, that is the syntax available in the behavioral modeling aims at the system level description. So here direct description of the design is not a primary construct, sorry, primary consideration, right? Direct description of the design is not a primary consideration in the Verilog standard, right? Okay, we get now. Direct description of the design is not a primary consideration in Verilog standard. So here we will be having the flexibility and versatility in design description, right? Describing the design. Okay. So here we always describe the design and simulate it for its functionality only. Okay. So really speaking, the Verilog HDL coding is very much easier than the VHDL if you are able to understand a little bit of C language concepts. Okay, but generally we have the practice of learning the VHDL first and then the Verilog HDL. Most of the industries will be using the Verilog HDL only, and we can't keep the VHDL aside since why? Because some of the components designs still has to be followed in the VHDL only. Okay, that is nothing but the hardware description language, right? Like HDL or VHDL, whatever it may be, everything is in hardware description language. Okay, so here we have different synthesis tools which will be offered by the different vendors. For example, uh, mental graphics. Mental graphics is going to give the models in the similar fashion. Xilinx is also give Xilinx will also provide you these synthesis tools. So these type of vendors, and not only this, we have Act2 HDL for the purpose of students for the freely availabilities. Act2 HDL. That's the tool name. Okay. Not only that, we also have some other one from Ultra. Ultra is also another company. We also have Quartus 2. Quartus 2 from Ultra. Model SIM from Mentor Graphics and Xilinx. Directly we can have. Out of these, generally we used to follow where we used to follow this Xilinx. Why? Because Xilinx is to give the full support. That means starting from the design description, we can do everything on the same tool. Okay, at some extent, and that means implementation with the help on the FPGA is not possible in this. We can't say not possible, but it may be possible, but it is not available in general, right? So generally, physically, if you want to verify your code on the FPGA is nothing but the field programmable gate arrays, right? If you want to do that, generally we used to follow this Xilinx. Xilinx is one type of vendor. Okay, Xilinx is a company, but vendors in the sense here we have to think the same, right? So most of the synthesis tools available from different vendors can synthesize most of the constructs at the data flow as well as the gate level, but not all constructs or the combinations possible at the behavioral level can be synthesized. Okay, behavioral level modeling cannot be synthesized by the all the vendors, right? So generally, if you write a code, all the code what you have cannot be all the code what you write cannot be synthesized. If the code is synthesized once, it is ready for implementation on the FPGA. You get now? The code whatever you write, it is possible to simulate and verify the functionality, but sometimes it may not be possible to synthesize the code what you write. You have to write a synthesizable code. You have to write a synthesizable code. Only that code will be implemented on the FPGA kits, right? So whatever the modeling style you may follow, either it is VHDL, whatever the language, either VHDL or Verilog HDL or System Verilog. The latest Verilog is the latest one is the System Verilog, which is used in industries, right? In the VLSI industries, we will be using this Verilog and System Verilog. Only some in some cases we will be using the VHDL also. Okay, whatever the code you may write, it may not be synthesized. We have to change the code once again and many number of times when we go for synthesis. If it is not synthesized for the first time, you have to change some of the statements and you have to synthesize it. Later, if it is okay, well and good. If it is not okay, then you have to change the once again. You have to change the code once again and then you have to synthesize it. Okay. So as we have seen in the data flow model also, operations and assignments, here also we have some operations and assignments in this behavioral modeling also. Okay. So procedural assignments. Okay. So the design description at the behavioral level is done through a sequence of assignments. These are called as procedural assignments. So in the contrast to the continuous assignments at the data flow level, so it seems to be like the assignments in a similar data flow, similar to that what we have seen in the data flow assignments. but it will be a little bit different. Okay, see here, the assignment is done through equal to symbol or less than equal symbol. Okay, this is the procedural assignment. This is the procedural assignment, whether we can use either equal to symbol or else less than equal symbol. We used to call previously it as continuous assignment, right? In the data flow model, we used to call it as continuous assignment. So equal to operator, you can see an operand specified on the left side of this sign. So what we can see here, we have an n value, it has been negotiated, and then that value has been assigned to n. Okay, so here the content of register n is complemented and assigned to the register n itself, right? Procedural assignment, right? Generally, what we have seen in the data flow model, we have seen that we have never used such type of thing. Okay, we have assigned some value to a, and then that value some value to the b, both has done some some operation with respect to the a is one variable and b is one variable. A is one operator and b is one operator. So in between that we have plus symbol, that means or operation, and it has given some value, and that one is stored in some other value, right? We have not assigned either to a or b. Okay, do you understand what's the difference between the both? So here we have a chance to do like this, right? So we have a value for n, and that one value, that n value is negotiated and it can be stored in n once again there itself, instead of using some other register, right? So the operations on the right hand can be involve operands and operators as in the previous data flow style. So these are logical operations, numbers, reals or integers also. These operands can be of different types: logical, variables, numbers, real or integers, and so on. Okay. So you have seen these operands in the table 6.1 to 6.9. That's the reason why I have discussed this data flow previously, right? The data flow model. Actually, in the syllabus, you have this data flow after the behavioral only. But for everything, we have to depend on that. So that's the reason why we have discussed that one first. Okay. The tables 6.1 to 6.9, the tables what we have seen in the previous 2 to 3 classes are that one only. So the same rules will be working in this behavioral model also. Okay, so the operands on the right hand side of the right hand side can be a net or a variable type. Okay, it can be a net or a variable type. They can be a scalar or vectors. It is necessary to maintain consistency of the operands in the operation. Okay, it's necessary to maintain consistency of the operands in the operation expressions, right? So here n is equal to m by l, where m and l have the same type of quantities, such as registers or integers or time, real time. Okay, that means if n has to have a value, generally this l and m both should have same type of. They both has to be of same type. If m is regarding the time in the nanoseconds, l also should be in the time. Okay, So may not be in the nanoseconds, but maybe a milliseconds. But totally, this has to be time, right? It has to be in the seconds only, right? So the operand which will be in the left side of this operator equal to has to be a variable, right? It is also should be a register, right? Generally, in the coding, if we are using a register, means that we are saying that we have the chance of varying it many number of times. That's the reason why we call it as variable. For that variables, we will be generally using these registers. Do you understand? So the one which one will be varying continuously will be generally a variable, right? For that we will be using the registers. So in the previously we used to use the wires, right? Why, even though we have mentioned it as a wire, but when we write the test benches, we will be mentioning those in the registers. Why? Because in the test bench, we will be continuously varying the input values, right? We will assign that for the same thing, we will be assigning different values. Then only we can get different varieties of outputs. For the different inputs, we will get different outputs, right? So it will be a register, but it will be a register, and we can assign it may be a scalar or a vector or a path vector or a concatenated vector. Path vector means out of 8 bits, if you consider only 4 bits, it is called a path vector. If it is, wait a bit. Okay. Concatenated vector means we will be concatenating one or more vectors or more bits. Then we'll have can have a bigger vector, right? We have seen all this in the previous class. Path vector means out of the 8 bits, we can take only 3 bits or 4 bits or 5 bits, like that. Okay, concatenating vector means we can take 2 or 3 or even a scalar also, single bit scalar also. Right. We also have here procedural assignments. These procedural statements are similar to the sequential statements in the C language. You can see the process statement in the VHDL there, but in the Verilog we can see here the procedural statements. That means we have generally in any of the programs we require some set of the statements has to be executed in the sequential manner. For that, there we have used the process statement. In the process, all the statements will be executed in the sequence one by one, right? So generally in the C language, everything will be executed in sequence only. So there we don't mention anything, process, procedural statements or anything, everything, but everything in the C language will be executing in a sequence. You can remember that once, right? So if it is like that, what happens is if all these statements in the program execute sequentially means it takes more amount of time. But we don't want to take that much amount of time. That's the reason why we have gone with this VHDL and Verilog HDL, where all the statements has to be executed within less amount of time. So that is all the statements will be executing concurrently. But the we already discussed in the VHDL that in the process statements for executing of the total statements it takes some amount of time. So that is the main time of the execution time of the total program. Right? So within that time only all the other statements will also be executing in the same fashion in the Verilog also, right? So you see here. So you see n is equal to m plus l, and n1 is equal to n multiplied with n. So this statement has to be executed in sequence only. Here you got the value of capital N from small m comma l, sorry, m plus l, right? Okay, that value has to be substituted in this capital N and small n. Okay, okay. Here, after getting the value here, that will be substituted here. That means if both executes in the concurrently, we don't find a value for n1. Okay, so here the process what is mentioned in the VHDL is now the always. Okay, what are the things present in the always block will be executed in sequence. So the above form a set of two procedures placed within always block. Okay, generally they are carried out sequentially in the order specified. That is, first m and m and l are added, and the result will be assigned to n, and the square of n is assigned to n1. So n multiplied with n means that is a square, right? Subsequently, the following assignments subsequent to the following assignments, if any, is carried out, or there can be exceptions to which will be discussed later. Okay. So the basic sequential nature of the assignments here is in the direct contrast to the concurrent nature of the assignments at the data flow level. So do you understand now this? In the data flow, we have not used this always statement, and that means that there we don't need to execute these statements to execute in sequence, right? Everything is independent there, right? But now here, everything has to be executed in a sequence if it is mentioned in the always block. Okay, so we have some procedural assignments in the process. Okay, the variety types we have to discuss that one later class. So in the next class, we'll see this functional bifurcation. So in this total class, what we have seen here is one thing we have identified which is different from the data flow. Okay, we can use either equal to symbol or else less than or equal to symbol in this. Okay, and in the data flow, we have not used this type of statements. Okay, we have not used this type of statements. Okay, this is possible here. Why? Because we are executing the always block where we can always block where we can have the sequence set of executing, right? So here we will be using the registers. Mostly we will be using registers, and for n, if you have some n will be having a value if m and l of both are of similar type. Right? If m is an integer, l also should be an integer. If m is some time, l should also be a time. If it is real, it is real. M is real, L is also should be real, like this. Both should be of same type. Okay, and we have seen that we have some procedural assignments. What we have in VHDL is just like a process. Here we have always block. The statements in this always block will be executing sequentially. Right? So functional bifurcation, you can see this functional bifurcation. This functional bifurcation we can see in the next class. Okay. See you in the next class.